Okay, and so lecture 2, and so this is attentional effects on stimulus processing. And so basically, if you're paying attention to a stimulus, how is this going to change the way that it's processed? And so the first thing we have to look at is auditory oddball test, which is a bit confusing. And the first thing to know about auditory oddball test is that they use an EEG to do it. And so you can think about that because an EEG goes over your head like a ball, and so auditory oddball had to do with EEG. And basically what that was is that the participants had 2 different earphones, and in each earphone, there was a series of sounds being played, and every once in a while, in each earphone, there would be an oddball, so a strange different sound. So like it would be da, 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 da. And so the high-pitched sound would be the oddball sound. And there was a different series being played in either ear, and what the participants were told to do was ignore one ear and only listen to the other ear, and every time they heard an oddball stimulus, to take note of it and press a button. And so then what they were going to do with this is they were going to compare the ERPs, or event-related potentials, between the 2 ears, because the 2 ears are are processed by different pathways in the brain. And so then when you break down the ERPs, they were looking at kind of 3 different categories. And so the first one is they were looking at early responses in the brainstem, and then they were also looking at kind of mid-time responses, so mid-latency responses in the auditory cortex. And so then basically the way that sound would make its way to your brain was first go through the brainstem, then through auditory cortex, and then finally was the late wave comparisons, which was in the auditory associative cortex, or remote sources, or in the frontal cortex. And so basically what you can draw from this is that as far as auditory stimuli, first it's going through the brainstem, then the auditory cortex, then the auditory associative cortexes, and kind of like weird things off to the side, like the frontal cortex or other remote things in associated cortexes. And another thing to know is the reason why they use EEG is because EEG is really good at recording things temporally. So you can really see if the event-related potentials are going to be early or late selected. And so then once this was all done, they looked at the results, and the results showed a couple different things, and they all have to do with different waves that are given different numbers. And so the first thing is that, number 1, attention enhances N100 waves. And this shows early selection. And so N100, early selection. N100, early selection. Okay. And attention enhances these N100 waves. And also, an effect can be seen in the P50 potentials, but not the brainstem. And so, basically, attention affects N100, and N100 shows early selection, and it also affects P50 potentials, but it does not affect the brainstem. And finally, P300 potentials are going to be late selection potentials. And so, and basically what they found was that these P300 potentials were increased over the parietal cortex for just the target sounds. And so when you heard a target sound, your parietal cortex would trigger these P300 waves. And so parietal cortex, P300, late selection. And then just to go back and review, N100 was increased by attention, and this shows early selection. P50 was also affected, but not the brainstem. And P300, which is late selection, was increased in the parietal cortex for just the target sounds. And then, if you're comparing it between channels, the N1 effect was much bigger around the attended ear. And there's kind of like a cowboy hat-shaped graph. And there's a little cowboy hat for the unattended ear, and a big cowboy hat for the attended ear. And the cowboy hat kind of looks like the RB symbol is right over the 100, because for the attended ear, this N1 effect is going to be at the 100, which is what we talked about earlier. And so the attentional effect is going to up the N100. And then also the P300 effect is a graph that kind of does little tiny sinusoidal waves, and then one big wave that goes up for the target ear, and one big wave that goes down for this non-target ear. And so that's showing the P300 effect, and so that's showing that P300 is late selection, and this is really, really strong for the target ear, and it's really, really negative and weak for the standard sound. And then the ERPs are just kind of in the middle for things behind the 300. And also, we're wondering if N100 has to do with the secondary auditory cortex. And you can remember this because if you get a 100% on the test, you're definitely not secondary. And so it's kind of like, it's counterintuitive. And so N100 has to do with perhaps the secondary auditory cortex. And P50, they are thinking is in A1. You can think about that because 50 is pretty much the lowest number listed in this. And P50 has to do with the primary auditory cortex. And so this would be primary auditory cortex is just kind of like a basic thing, and so you can connect that to P50. Okay, and then finally, the fMRI results of this test show that the effects of attention on auditory stimuli are mostly relevant in the auditory belt. And so just to go over everything, N100 waves show early selection, and these are affected by attention. P50 waves, which might be in the A1 because it's a low number and A1 is pretty basic, are also affected, but not in the brainstem. P300, which show late selection, increase their potential over the parietal cortex for target sounds, and this is centered around kind of 300 milliseconds. And then finally, fMRI says the largest effect of attention in attention affecting auditory stimuli is in the auditory belt. And then just go back, I don't think I said this, N100 might be in the secondary auditory cortex, because if you get 100% on a test, you're definitely not secondary. And so the N is for not the secondary auditory cortex. 100%, you're not a secondary student.
Okay, and so another auditory attention thing is the mismatch negativity, or MMN, and this is when you're kind of expecting a tone, and then the tone that you get doesn't match what you're expecting. So maybe you're listening to Jingle Bells, and then all of a sudden there's some really high, unpleasant note in the center. That's called a mismatch expectation, and a mismatch, or a mismatch negative, and that effect is amplified by attention. And so moving away from auditory and into visual, visual spatial attention also evokes ERPs, just like we talked about earlier. So N1, P1, that's also in there for visual. And visual attention is strongly lateralized over early visual regions. And so this is the opposite of auditory, which isn't lateralized. And visual is contralateral, as we know, because the eyes cross. And basically what we're going to find is that there's a stronger ERP when you attend to the visual area that the stimulus is going to pop up into. So basically, if you think that the stimulus is going to pop into the right of the screen, and so you start looking at the right of the screen, it's going to evoke a stronger ERP because of that. And another thing to know is the re-entrance activity. And so basically what this is that the information from a visual stimulus goes through the brain twice, once at about 100 milliseconds and another time at 250 milliseconds after the stimulus. And so people think that the 250 afterwards is for additional kind of more detailed analysis. And another thing to know finally is that fMRI is good for spatial resolution, so kind of like seeing what's going on in the brain, but it's really bad for temporal, so you're not really going to be able to tell late versus early responses with fMRI, so that's something to keep in mind. fMRI isn't good for timekeeping. And then another thing that has to do with visual spatial attention is retinotopic mapping, and so basically what that is that spatial attention is modulated early, modulates early visual processing, so that's V2 through V4, and it does it in a retinotopic way. And so spatial attention has to do with retinotopic mapping in V2 through V4, just to sum that up quickly. And then finally, one more piece of information is that the fMRI shows the effects of attention on visual stimuli in the V1 and in the thalamus. And so basically, if you pay attention, you're going to have a higher response evoked in the V1 and in the thalamus. But this might also just be because of reentrance, which we talked about, which is it goes through the brain once at 100 milliseconds and another time at 250. And another thing to know about attention, it's not necessarily a concept, but it's just something to know, is that attention doesn't increase the selectivity of visual neurons. And so basically it's not going to, attention in the visual sense won't enable you to select for something, but and it also doesn't sharpen the tuning curve. But what it does do is multiplicative gain, and so that means that at the attended place, if it's the correct thing that you're looking for, so attended place, correct thing you're looking for, there's going to be a higher number of spikes. And so that's multiplicative gain. And so just to go over it really fast, fMRI is not good for spatial. fMRI shows that there's attentional effects in the V1 and thalamus when you're looking at visual stimuli, but that might be because of reentrance. And also, attention doesn't increase the selectivity, does not sharpen the tuning curve, but does increase multiplicative gain, which is more spikes when you're attending to something and when you see something that you have been looking for. Okay, and so another thing to know is that if you pay attention to something, it's going to be even more effective depending on the contrast. And so things that are heavy contrasted, attention isn't going to do as much. But if there's a low contrast and you pay attention, that's going to make a world of a difference. And so basically what it is there's a strongest effect of attention on visual stimuli for low to mid-range contrast. And that's probably because, like, think if you see kind of really faint words, attention is really going to help you understand those words, whereas if the words are solid black on white, you really don't need attention to kind of pay good attention to this. And this is in a graph that kind of looks like a triangle with the top cut off, because there's a little peak at the top in the mid to low range contrast that it's the highest and it's like the best for you to pay attention there. And so basically low to mid range contrast is going to benefit the most if you look at, if you pay attention to something with mid to low contrast, it's going to be the most beneficial. Also, it's good to know that visual stimuli compete in a biased competition way. And so basically, two different stimuluses are going to compete for who gets the most attention or the most cognitive resources allocated towards it. And so that's biased competition. And finally, we're moving on to feature-based attention. And so basically, this has to do with the fact that the first thing to know is that if you're paying attention to motion, you're going to see activity in the brain region that kind of like processes this. Like, for example, if you're looking at motion, you're going to see an increased firing rate in places like the MT. And these are called the extrastriatal visual regions, and they coordinate back to kind of whatever you're observing. So once again, motion is going to see an increase in the MT. And another thing to know is that spatial attention enhances activity in the visual cortex in a spatial manner. And so basically you pay attention to something in a spatial way, and this is going to be translated back into the V1 in kind of a spatial manner. And then these two effects, which are basically like these corresponding extrastriatal visual regions, are going to experience elevated activity if you're observing something related to them, and also that spatially it's going to translate back into a spatial V1 interaction. These are additive. And so that means that they can both kind of enhance each other. And so that means that they are independent processes. And then another thing to know is that feature processing is kind of a global thing. And it's good to know that it's kind of all across the brain, because for feature-based, so like if you're looking for a red shirt, it's going to enhance these neurons that are looking for that all across the brain. It's not just in a spatial manner or only in one spot. It's across the whole brain, and so it's pretty global. And then another thing to know is that if a response to an ignored stimulus will increase if the ignored stimulus matches something. And so we've been over this before. So basically, like if you're looking for a green leprechaun and you see a purple leprechaun, even though you're supposed to be ignoring that, it's going to be increased because it's still leprechaun. And another thing to know is that Bichotte, who did some bitchy experiments, did experiments with monkeys, and he basically discovered that if he told them to search for a certain color and shape, they would fire the most, or their neurons would fire the most, when they saw that specific color and a specific shape. And so he's pretty bitchy because that's a pretty fucking obvious experiment, and that's kind of mean that he put monkeys through that. The final parts of visual attention to know are have to do with object-based attention. And so basically, we've kind of been over a lot of this. If you see an object, the activity in the specific brain region correlated to that object is going to be increased. For example, if you see a face, the fusiform facial region will be even more activated. And then also fMRI data shows that if you pay attention to one part of the object, your attention is going to kind of spread over the whole object. Again, we've been over that too. And then also this has a relation to the perceptual load. And so basically they did a test where they overlaid a face over different backgrounds that were complicated and not complicated, and they saw kind of the response in the brain to this, and then they showed some of them multiple times, and basically what they concluded is that you get repetition suppression only in the low load. And so basically if you have a low cognitive load, your brain is going to be able to not have as high of a response the second time around that you see that. But if it's a high cognitive load and you have to take a lot of work processing it, you're not going to be able to get that repetition suppression. And if it's a difficult thing that you're processing, the second time you see it, you're not going to have a reduced response because it's so difficult to process. And they did this with faces overlaid in architecture-y house type things. And this was in the parahippocampal parahippocampal area, which is the PPA.